In last lecture, we have derived Lagrangian equations of motion for a central force field. And the first Lagrangian equation of the motion was mr double dot minus mr theta dot square plus dv by dr is equal to 0. So this was the first equation, and d by dt of mr square theta dot is equal to 0. So this was the second equation. So as the derivative of this term is 0, so this term must be constant, and we have calculated that term constant as L. Therefore theta dot is equal to L upon mr square. Just put this value of theta dot into this equation. So the equation 1 will become mr double dot minus mr L square upon m square r raised to 4 plus dv by dr is equal to 0. So 1 m will cancel, 1 r will cancel. So mr double dot minus L square upon mr cube plus dv by dr is equal to 0. Now mr double dot will be equal to minus dv by dr plus L square upon mr cube. So as this mr double dot is nothing but m into a, which is a kind of a force, therefore let us call it as mr double dot is equal to f dash of r. So I can write it here, f dash of r is equal to f of r plus L square upon mr cube minus of f of r. So here you can see that, so this f dash is a effective force, which is a combination of the central force and L square upon mr cube is nothing but the centripetal force which is required for the orbital motion. So I will write this term as a centripetal force. So the effective potential created by the central force and the effective potential created by the centripetal force is nothing but the effective potential for the total central force field which is performing orbital motion. If this is the force, then the V effective is given by integration of minus f dash of r, which we can write it as a, put just value of this f dash r as integration of f of r, or first I will write as it is minus of f of r plus L square upon mr cube into dr. If you don't skip the steps, you will get the accurate answer. Now see here, so this V effective is equal to integration of f of r dr. So this minus and minus will become plus, minus integration of L square upon mr cube dr. So this is nothing but the V of r and plus L square upon mr square. So this is the V effective for the central force field, out of which, so this is due to the central force field and this is due to the centripetal force. So this term is coming from the central force and this term is coming from the centripetal force. Now if I take the gravitational force field, so this gravitational force field potential, it can be written as, or it is a function of minus k by r. So this term can be replaced by minus k by r for the inverse square law. This we have calculated in a previous lecture, how this v of r can be replaced by this minus k by r. So v effective is equal to minus k upon r plus L square upon mr square. Now this sign of k will decide the nature of the force. So this sign of k will decide nature of force. We know that this inverse square law, which is a gravitational law, one example is a gravitational law. Okay, so this is a attractive potential, so we can write that negative k will represent the attractive potential, and this body will perform a bounded motion. Similarly, if the k is positive, so it will represent the repulsive potential, and the body will perform unbounded motion. And if the k is a 0, so there is no potential between the incoming particle and the central force field. Now let us draw the diagram of the effective potential versus the distance between the central force field and the incoming particle in the central force field. So this is a V effective, this is R. We know that this V effective is addition of this minus k by r and L square upon mr square. This L square upon mr square, this is a exponential decaying function, and I can draw it like this. So this is nothing but L square upon mr square, and minus k by r, this is a increasing function like this. So this is minus k upon r, and if I take the effective potential of these two, so this will give me the graph like this. Somewhat nature will be like this. So this is the effective potential due to the central force and due to the this is centripetal force, and this is due to the central force. Now this is the effective potential by the combination of these two. Now suppose there is a particle which is entering into the central force field. So its energy is say E greater than 0. So this particle will be scattered from the central force field, as it is having only one intersection over here. So I'll write it here as a R1 and this as a E1. So for this, so scattering will be there. Now if I have any particle which is E2 is equal to 0, this is also intersecting the effective potential only at a one point, and I will call it as R2. So this will form, or this will perform parabolic path, which is given by this R2. I'll write it here, parabolic path. Now if I have some another particle which is having energy E3, so this E3 is so this greater than V effective but less than 0. Okay, if this is the situation, or if this is the kinetic energy of the incoming particle which is greater than this V effective but less than 0, then this particle will form a bounded motion. These two are unbounded motions. So these two are unbounded motions, whereas when this E3 is less than 0, we can see that this is interacting this effective potential graph at 2 points. I will call them as R3 and R3 dash. It means that it is performing an elliptical orbit. Elliptical orbit. And suppose there is another particle which is E4 is equal to V effective. So such a type of a particle whose energy is nearly equal to the V effective, then it will follow the orbital path or the circular path. Now see here, whenever a particle is entering into the central force field, suppose this is the center of the central force field and it is its potential field. I'll write it like this. And if there is a particle coming inside this potential field and if it is having energy E1 greater than 0, then it will be just scattered from here. So it will not enter much deeper into the central force field. So it will just be scattered and it will form an unbounded motion. Even if there is kinetic energy of the incoming particle E2 is 0, it may also follow the parabolic path. Suppose the particle is coming from this side, so it will go from this side and it will follow the parabolic path, which will be also the unbounded motion. If the energy of the particle is greater than effective potential but less than 0, then it is intersecting this V effective potential at the 2 points. It means that it is following an elliptical orbit and it will start revolving around the center of the nucleus and it will in the elliptical orbits. If there is another particle whose energy is nearly equal to the effective potential, then that particle will follow the circular path around the central force field. Okay, so this equation V effective, this sign of K and the energy, so these will decide what kind of a motion the particle will perform when it enters the central force field. And this is the diagram which is mostly published on the cover page of the classical mechanics, so which suggests the importance of this figure, because the classical mechanics central force field plays a crucial role, and this is the diagram which explains the path of the particle into the central force field. We can write it in a tabular form also. So suppose I have E is the energy of the particle, so I can have the 4 conditions: E greater than 0, then E is equal to 0, E less than 0 but the greater than V effective, and E is equal to V effective. For such cases, eccentricity E is given by, so this eccentricity E is greater than 1. For this eccentricity E is equal to 1. So this is 0 less than eccentricity less than 1, and here eccentricity E is equal to 0. So the nature of the orbit will be hyperbolic. So this will be parabolic path. So such type of a motion will be elliptical orbit. This is a circular orbit. So the moral of the story is the potential of the central force field and the energy of the incoming particle will decide the nature of the orbital motion in the central force field.